Hello, this is Dr. Habib Ahmed, and today I am going to demonstrate the Silvaco TCAD simulation of high power aluminum nitride based PIN diodes. So I'm going to demonstrate the simulation of aluminum nitride based PIN diodes with I layer thicknesses of 0.5 micrometers, 1 micrometer, 2 micrometers, 5 micrometers and 10 micrometers. Initially, I'm going to simulate the Silvaco TCAD simulation of aluminum nitride based PIN diode with an I layer thickness of 2 micrometers, and then I'm going to show the results of other structures as well. Aluminum nitride is a wide bandgap material. Its bandgap is approximately 6.2 electron volts. If you compare the performance parameters of aluminum nitride with other semiconductors, you will find out that aluminum nitride is either the best or second best as compared to other semiconductors in terms of high power semiconductor device potential. The critical electric field of aluminum nitride is approximately 15.4 megavolts per centimeter. If you compare it with its contemporary wide bandgap materials, you will find out that this critical electric field is approximately 1.5 times as compared to that of gallium oxide, 3 times as compared to that of gallium nitride, and 5 times as compared to that of silicon carbide. Until recently, the major limitation was achieving p and n-type doping in aluminum nitride, but our group at Advanced Semiconductor Technology Facility at Georgia Institute of Technology, run by the wonderful Professor William Allen Doolittle, have demonstrated both p and n-type doping for aluminum nitride, and we have published a lot of papers based on that. As you can see over here, beryllium acts as a p-type dopant and silicon acts as an n-type dopant in aluminum nitride. And this is one of the figures from our papers. So, if you compare the critical electric field of aluminum nitride with gallium nitride, it's approximately 3 times larger as compared to that of gallium nitride. And based on that result, the Baliga's figure of merit for aluminum nitride is approximately 17.5 times as compared to that of gallium nitride based devices. Similarly, in terms of Johnson's figure of merit comparison, for aluminum nitride based devices, it's approximately 3 times higher as compared to that of gallium nitride based devices. Baliga's figure of merit and Johnson's figure of merit are both metrics used to evaluate the performance of power semiconductor devices. Now, I'm going to demonstrate aluminum nitride based high power PIN diode. So I will show the simulation of aluminum nitride PIN diode under forward bias and later under reverse bias as well. High power PIN diodes find applications in various fields due to their unique properties such as high breakdown voltage, high thermal conductivity, and high switching speeds. PIN diodes play a crucial role in various high power and high frequency applications where efficiency, speed, and reliability are essential requirements. Some common applications of high power PIN diodes are radio frequency power amplifiers, power supplies and converters, pulse power systems, switching devices, high frequency circuits, medical equipment, laser diode drivers, high power microwave systems, etc. The reverse breakdown characteristics of high power devices play a crucial role in ensuring their reliable operation, protecting them against over voltage conditions, minimizing power losses, and enabling efficient performance in various high power applications. High power devices often operate in applications where they need to withstand high voltages without breakdown. Reverse breakdown voltage is the voltage at which the device starts to conduct significantly under the reverse bias condition. So high reverse breakdown voltage is essential to ensure the device can block the applied voltage effectively and prevent unintended conduction, which could lead to device failure or damage. So it's an area of high significance. So that's why I planned to demonstrate the Silvaco TCAD simulation of aluminum nitride based high power PIN diode. Let's start talking about the code now. So I am going to create the structure in the Athena module of Silvaco TCAD, and then we will look at the IV characteristics of the device at this module of Silvaco TCAD. Initially my structure is running from 0 to 5 micrometers in the X direction. So like from here to here. Why do we see it until like 10 micrometers? Because later I'm going to mirror the structure, so it's going to be extended up to 10 micrometers. Similarly, initially my structure is running from 0 to 1 micrometers in the Y direction, and here are the spacings for my meshing. I have introduced silicon as a donor impurity in aluminum nitride and beryllium as an acceptor impurity in aluminum nitride. And this is what worked for our group at Georgia Tech as well. I'm talking about Dr. William Allen Doolittle's group. We experimentally achieved N-type aluminum nitride with silicon doping, and we achieved P-type doped aluminum nitride using beryllium doping. So I initiate a substrate of aluminum nitride with N-type doping of 6 into 10 to the power of 18 per centimeter cube. I'm going to go to display, click contours, and then click OK. So this red layer, which is running from 0 to 1 micrometers, has an electron concentration of 6 into 10 to the power of 18 per centimeter cube. Then I'm depositing another layer which is 2 micrometer thick. It has silicon doping, and its doping level is 1 into 10 to the power of 16 per centimeter cube. So as you can see, it's a 2 micrometer layer with the electron concentration of 10 to the power of 16 per centimeter cube. Then, and this is my I layer. Then I deposit a 0.5 micrometers thick aluminum nitride layer doped with beryllium at a whole concentration of 3 into 10 to the power of 18 per centimeter cube. So this top layer is doped P-type, as you can see from this color chart, and its carrier concentration is 3 into 10 to the power of 18 per centimeter cube. Now, why did I choose these values, like 6 10 to the power of 18 for this layer, 1 10 to the power of 16 for this layer, and 3 10 to the power of 18 per centimeter cube whole concentration for this layer? There is a reason for that. So I'm gonna take you to a couple of my papers. This paper is about achieving P-type aluminum nitride using beryllium doping. And I grew ton of samples in this study, and from the results, like I achieved a maximum whole concentration of 3 into 10 to the power of 18 per centimeter cube. So that's why I have chosen a whole concentration of 3 10 to the power of 18 per centimeter cube for this layer. Now I'm gonna take you to another paper. Here we have demonstrated N-type doping of aluminum nitride, and we also demonstrated homojunction PN aluminum nitride diode. As you can see over here, this is me in the author list, and this is my advisor, Dr. Doolittle. So in this study we demonstrated, I want to look at the table which shows silicon doping of aluminum nitride. Should be pretty obvious. Oh, here it is. So here I achieved a maximum electron concentration of 6 into 10 to the power of 18 per centimeter cube, and then we demonstrated aluminum nitride based devices as well, as you can see over here. These are one of a kind of pioneering results. Okay, so that's the reason I've chosen these carrier concentrations to kind of replicate the experimental results. Then I deposited a 0.2 micrometers of platinum on this structure. So here is the platinum, and this is the orange layer is the platinum layer. And I etched the platinum to the left of 2 micrometers. So as you can see, this is the 2 micrometer point. I etched it to the left of 2 micrometers. Then I deposited, I don't need this over here. Then I deposited a 0.3 micrometers oxide layer, and I etched it to the right of 4 micrometers. So I deposited 0.3 micrometers oxide layer. As you can see over here, it's running from 2.7 to 3. And I etched it to the right of 4 micrometers. So as you can see, initially my structure is running from 4 to 5 micrometers. Okay, from 1 to 5 micrometers. Initially, like this is my initial structure running from 0 to 5 micrometers, and I etched the oxide layer to the right of 4 micrometers. This makes half of my structure. Then I use this command of mirror to mirror the structure to the right. So now it extends from 0 to 10 micrometers with a beautiful representation. I have defined this point as the anode and the back side of the structure as cathode. So this platinum layer is being assigned as anode, and the back side of the structure is assigned as cathode. Then I create the structure file. I start working Atlas module now. I import this structure which is already created in Athena, and I define some material properties for aluminum nitride: its band gap, electron affinity, permittivity, density of states in the conduction band and valence band, electron and hole mobilities, and electron and hole lifetimes. Then I introduce certain models for the simulation. Bipolar band-to-band tunneling. This model is really crucial for reverse breakdown simulation of the structure. Similarly, this model, which represents Silvaco impact ionization, is really crucial for reverse breakdown simulation of the structure. Then I want to look at certain output parameters, energy levels, current flow lines, etc. Then I will introduce Newton method for numerical simulation of the semiconductor device. Here I save the structure under thermal equilibrium. In this block of code, I'm running the structure under forward bias, initially from 0 to 5.5 at a step of 0.1 volts, and then later from 5.5 to 7 at a step of 0.05 volts. Then I want to run the structure under reverse biasing by using this block of code using curve tracing. So here I want to run the structure under reverse bias and keep increasing the voltage until the current arrives at 1 milliamps. So I start with 0.01 volts, and each subsequent step is multiplied with 1.02. So the voltage is going to keep increasing. Similarly, the current is going to keep increasing until the current arrives at 1 milliamps. And then we solve the Cur trace, save the results, and plot the results in a log file. So this is the code for this structure. Now I'm going to run the simulation. Here is the structure under thermal equilibrium. We can right click on the structure, go to contours, click on contours, go to define, click contours, and click on current flow lines. Initially there are no current flow lines inside the structure because this is under thermal equilibrium. So you would see random lines, but not like organized lines running from the anode to the cathode. However, we can look at certain other parameters. For example, net doping, as you already saw. So we go to display, hit define, go to contours, linear, then did I choose something else as well? Go back to contours, net doping, log, we go to absolute net doping, okay. Here is the IV characteristic under forward bias. So if some sort of technical error came, that's why I'm going to run the simulation once again. Here is the structure once again. I go to display, I go to contours, go to define, contours, and then I go to net doping, hit apply. Yeah, now it's working. For some reason it stopped working. I was not able to see the net doping. Don't know why, but things happen sometimes. Funky things happen. So you gotta restart. These are the doping levels. You can draw a cut line across the structure to see the exact doping levels. 3 10 to the power of 18 for this p-type layer, 1 into 10 to the power of 16 for this layer in the center, the yellow layer, and 6 into 10 to the power of 18 per centimeter cube for this red layer. We can go to display, and see the energy band diagrams. Energy band diagrams are crucial, that's why I focus a lot on energy band diagrams. Band gap engineering is really crucial for devices. If you understand band gap engineering, you can pretty much design any kind of device. So here you can see that this side over here is the p-type layer, this is the I layer, and this side over here is the n-type layer for the aluminum nitride. Then here is the forward bias IV characteristic for this figure. So you can go to display, and I want to see anode voltage versus anode current. So we can see that the turn-on point of this aluminum nitride based PIN diode is approximately 6 volts, and we are running it up to 7 volts. At 7 volts the current is approximately how much? It's approximately 186 milliamps. Now we want to see the simulation of this structure under reverse bias as well. So we are at curve tracing. The voltage is increasing at multiplication factor of 1.02. So as you can see over here, the voltage has increased to approximately 26 volts, 27, 28, and it's going to keep increasing until the cathode current arrives at 1 milliamps. So we have kind of set the breakdown current to 1 milliamps. So let's wait and watch until this curve tracing is finished. Okay, as you can see over here from this plot, so we are going to go to display. We want to see cathode voltage versus cathode current, and we had apply. So the current at this point over here is 1 milliamps, and at this breakdown current the voltage is approximately 472 volts. So 472 volts is the breakdown voltage for this case, where the I layer thickness for the aluminum nitride PIN diode is 2 micrometers. So these were some results. Now I also told you that I'm going to show you the results for I layer thicknesses of 0.5, 1, 5 and 10 micrometers. I'm not going to simulate each and every one of them. Also, I've simulated an aluminum nitride homojunction PN diode structure. As you can see over here, the I layer thickness in this one is 0. So The breakdown voltage for this one is approximately 13 volts, pretty low as compared to the PIN diodes. Now let us go to 0.5 micrometer eye layer thickness based aluminum nitride PIN diodes. And for this case, the breakdown voltage has increased to approximately 130 volts. Now for 1 micrometer, the breakdown voltage is approximately 245 volts, I would say. For 2 micrometer, we already saw it's 470 volts. For 5 micrometer, this breakdown voltage is approximately 1000 volts. And for 10 micrometers, the reverse breakdown voltage is approximately 1500 volts. So that concludes the session for today. I hope this was a useful video for you. Until next time, adios.